So in this video, we're going to start talking about chemical equilibrium, which comes after kinetics. So we said that kinetics is concerned with the rate of a chemical reaction, the factors that influence how fast a reaction goes, the rate law, so forth. Equilibrium is concerned with the extent of a reaction. In other words, how far does a reaction go? Very often you'll see a reaction that does not go to completion. It may only go partially to completion and then stop. And you'll wind up with a mixture of both products and reactants. So as an example, this is used in all the same example is used in almost every Gen Chem textbook I've ever seen, is the reaction between N2O4 and NO2. Okay, so N2O4, they're both gases. N2O4 is colorless and NO2 is brown. Okay, so this is an equilibrium system. Okay, naturally exists as a mixture of the two. So if a flask is filled with pure N2O4, so in other words, we're going to come in, we're going to take a flask, we're going to put nothing but N2O4 in it. There's no NO2. And we seal it up, and we come back the next class period, we're going to find out that some of our N2O4 was converted into NO2. That we now have a mixture of the two. Okay? And then let's suppose if we come at it from the other end, let's suppose we come in, we have a flask and we fill it up with NO2. There's nothing but NO2 in there, there's no N2O4, we seal it up, nothing can get in or out, we come back, we find a mixture of NO2 and N2O4. In other words, some of our NO2 would have been converted into N2O4. And then furthermore, if we come in, no matter which N we start with, whether we start with pure N2O4 or whether we start with NO2, what we're going to find out is, if we've given it sufficient time to come to equilibrium, that the ratio of N2O4 to NO2 in the two flasks would be the same, regardless of whether we started with pure N2O4 or NO2, right? So at a given temperature, the ratio of NO2 to N2O4 is a constant once the equilibrium has been established. Okay, so what's going on here? We have two reactions taking place at the same time. First of all, I want to comment, let me back up here and want to comment on something. Okay, an equilibrium is not a static situation. Okay, it does not mean that once equilibrium has been achieved that the reaction stops. Okay, what it means once you've achieved equilibrium is there's no further changes in the concentration. Okay, so in other words, the conversion of N2O4 into NO2 is balanced by the conversion of NO2 back into N2O4. So you might have these two sitting here switching back and forth, but once the equilibrium has been achieved, the concentration doesn't change. But it's not a static situation. Reaction hasn't stopped once the equilibrium has been achieved. So what's going on here? So we have, obviously then we have two reactions taking place at the same time. The conversion of this into this and the conversion of this into this. Right? So the rate of the forward reaction, we'll call this the forward reaction. Okay. The conversion of N2O4 into NO2 will be some rate constant times the concentration of N2O4, and the rate of the reverse reaction will be some constant times the concentration of NO2 squared. Okay. See, so what's going to happen is, let's say we start with let's say we start with some pure N2O4. Okay, so there's no NO2. And we put pure N2O4, we put pure N2O4 into the flask. Okay, and it's going to start out fast, right? Rate's going to depend on concentration, right? So it's going to start out fast and slow down. Okay, so it starts out fast and begins to slow down. And then what happens is, once the N2O4 begins to make NO2, then the NO2, concentration of NO2 builds up, and the higher this becomes, then the greater is going to be the forward rate. So this reaction, if we start with pure N2O4, this reaction will start out fast and slow down as this drops. And this reaction will start out slow and get faster as this increases. And we're going to get to the point where once the equilibrium has been achieved, then that the two reactions will be going at the same rate. So one more time, this one will start out fast and slow down as this drops. This reaction will start out slow and speed up as we get more in NO2. And then once the equilibrium has been achieved when the two processes are occurring at the same rate, right? So one more time, it's not a static situation. It's not completely frozen, but once the equilibrium has been established, these concentrations don't change because the two reactions are occurring at the same rate. Okay, so what we're going to do is we're going to take the ratio of the two rate constants, or of the two rates rather. So the rate constant for the forward reaction times this concentration is equal to the rate constant for the reverse reaction divided by, or times the concentration squared, right? So we rearrange it and say the rate of the forward reaction divided by the rate of the reverse reaction is basically concentration of NO2 squared over N2O4. Okay, and then the ratio of the forward rate constant for the forward reaction divided by that of the reverse is K. We call that the equilibrium constant for the reaction. And this is a constant for a particular reaction at a particular temperature. Okay, it is temperature dependent, because when you change the temperature, you're going to change the rates, and therefore the equilibrium constant will be different. Okay, so what is the significance of the magnitude of K? Okay, so if K is very large, reaction goes far to completion. In other words, the position of the reaction favors products. Okay, let's use a simple example. Let's suppose we simply have A makes B. Reactant A makes product B. And the K would be concentration of B over the concentration of A. It's always products over reactants, right? So if this reaction lies far to the right, that means this concentration will be large. And this concentration will be small, right? And so a large number divided by a small number is a big number, right? A small number divides into a large number, that makes a big number, so K is going to be big. So you can see then, by the way we're setting this up, as products over reactants then, okay, the further the reaction lies to the right, the bigger the K is going to be, because of the way this is set up, okay? So conversely then, if K is small, that indicates a reaction that does not go far to completion, right? So we stick with our same reaction. A makes B, and K is concentration over B, and I should have used double arrows here, by the way. Use double arrows with equilibrium. Anyway, K is concentration over B over concentration of A. Now, if this reaction lies to the left, it's mostly over here, then this concentration, the concentration of the product, will be small, and the concentration of the reactant A will be large or larger. So now we have a small number divided by a larger number, and that gives you a small number. Okay, so K is large, that indicates a reaction that goes far to the right. If K is small, that indicates a reaction that lies to the left. Okay, and then, of course, the third case, if you have close to 1, in equilibrium, concentrations and products are nearly equal. Okay, so what we call the reaction quotient, which is Q, is a ratio of terms consisting of product concentrations divided by reactant concentrations, with each raised to the power of their balancing coefficient. So if we have some general reaction, D plus E makes F plus G. Okay. The lowercase letters are the balancing coefficients, and the uppercase letters would be formulas, right? So our reaction quotient is constant. One more time, it's always products over reactants. So the concentration of F raised to the F power times concentration of G raised to the G power divided by concentration of E to the E power times concentration of D raised to the D power. Now, you have three cases. Q can be equal to K, okay, which means the system is at equilibrium. Okay, system is at equilibrium. There will be no shift in the reaction. If Q is less than K, the reaction is going to shift to the right. Now, remember this. A system that is not at equilibrium, it will shift until it is at equilibrium. So let me write this. I'm going to write this again over here. So Q is concentration of F raised to the F power times concentration of G raised to the G power divided by concentration of E to the E power, lowercase e power, times concentration of D to lowercase d power. So if Q is less than K, okay, well, if Q is less than K, that means the reaction that means Q is too small. Q is too small. So what can make Q bigger? Will a shift to the left or a shift to the right make Q bigger? Well, if the reaction shifts to the right, what's going to happen? As it shifts to the right, these numbers will become bigger. These numbers will become bigger, and these numbers will become smaller, right? So that shifting to the right makes Q increase. Shifting to the right makes Q increase. So if Q is less than K, it's not at equilibrium. It's going to react until it is at equilibrium. How is that going to happen? By the reaction shifting to the right. Okay. So conversely, if Q is less than K, then it's going to shift to the left. I'm sorry, Q is bigger than K. So if Q is bigger than K, that means Q is too small. That means Q has to go down. If this term is too big, that means these are too big and these are too small. It means it's going to shift to the left so that these go down and these go up. So if Q is equal to K, it's at equilibrium. If Q is less than K, it will shift to the right. Q is bigger than K, it'll shift to the left. Okay. So So let's talk about how we manipulate equations for chemical equilibrium, because there might be times where you want to do this. Okay, first of all, if you change the direction of an equilibrium, the new equilibrium constant is the reciprocal of the original. For example, the reaction that we started with, two NO2s in equilibrium with N2O4. Alright, so our first K, K1, is concentration of N2O4 divided by concentration of NO2 squared. We wrote the reciprocal of that, which is N2O4 in equilibrium with two NO2s, then K, this K, is concentration of NO2 squared. Coefficients become the exponents divided by N2O4. Okay, that should be a subscript there. N2O4. We should be able to say this number is a reciprocal of the other. Simply by the way we've set this, while we're setting all this up mathematically, if you reverse a reaction, that what was on the top becomes on the bottom, and vice versa. So the new equilibrium constant is a reciprocal. Okay. A second thing is you multiply by a number. The equilibrium constant is raised to that power. So for example, if we look at the reaction, phosphorus trichloride plus chlorine gas makes phosphorus pentachloride. The first equilibrium constant, or the equilibrium constant for this reaction, right, products over reactants, so concentration of PCl divided by concentration of Cl2 divided by concentration of PCl3. Okay. If we multiply the whole reaction through by 2, it's the same reaction, except the way we write these equilibrium expressions, the coefficients become the exponents. We put a 2 in front of the reaction, those 2's become powers. Right? So this equilibrium constant is the square of this one. So in other words, K2 is K1 squared. And next thing is adding chemical equilibrium. When you add chemical equilibrium, the equilibrium constants are multiplied. So let's say we look at two reactions. 2N2 plus O2 makes 2N2O. Then our first equilibrium constant, one more time, it's products over reactants, and the coefficients become the concentrations are raised to the power of the coefficient. So concentration of N2O squared divided by concentration of N2 squared times O2. Okay, and we second reaction. N2O plus 3O2 makes 4NO2. So concentration of NO2 raised to the fourth power times concentration of O2 raised to the third power times concentration of N2O raised to the 2th power. Now, if we add these two reactions up, our N2Os would cancel, and be left with 2 N2s and 4 O2s make 4 NO2s. Okay? And if we write the equilibrium expression for this reaction, then it's N2O4 to the 4th power divided by O2 to the 4th power divided by N2 to the 2nd power. Okay? So this equilibrium constant is the product of these first two equilibrium constants. In other words, K3 is K1 times K2. So let's talk a little bit here now about gaseous reactions. So far, So far in every example that I've used, we've used concentration. Remember, those brackets always indicate concentration. But we could also use pressure. So gas for gaseous reactions. So gas concentration is directly related to the partial pressure. So we could substitute partial pressures into the equilibrium expression. We could use pressures instead of concentrations. All right, so let's look at this reactions. Haber process, this is how they make ammonia, is the equilibrium reaction between nitrogen and hydrogen gases. Nitrogen plus hydrogen makes ammonia. So Kc, now I'm using C to represent concentration. Remember, one more time, brackets indicate concentration. So Kc would be concentration of NH3 squared divided by concentration of H2 cubed divided by the concentration of N2. Okay, and you realize also that it's divided by the product of those two. So what if we used Kp? What if we used pressures? If we used pressures instead of concentrations, we could do that. But we would get a different number. It's like expressing the same thing in a different unit. So we could use pressure of NH3, partial pressure of NH3, and partial pressure of H2, and partial pressure of N2, but otherwise do the calculation the same. We'd get a different number, but like I say, it's just like measuring a length in feet instead of meters. It's just basically a different unit. All right. So Kp is not numerically equivalent. You're not going to get the same number, but they can be related by this expression. Kp is equal to Kc times RT to the delta times the product of RT raised to the delta Ng power, right? So delta Ng, just basically, it's the change in the number of moles. It's the moles of gaseous products minus the moles of gaseous reactants. R is the gas constant, 0.08206. Liter atmospheres per Kelvin mole, and T is the Kelvin temperature. Right? To be consistent with units, T is going to have to be in Kelvin because that's the temperature and the gas constant. So let's work an example. The manufacture of methanol. Okay, so carbon monoxide plus hydrogen, so gas, all of them are gases, makes methanol. All right, so suppose I tell you that Kp was 3 times 10 to the minus 2 power at 200 Celsius. We want to find Kc. Okay, so we have 1 mole of gaseous products and 3 moles of gaseous reactants. So delta Ng is minus 2. We always do any change, I've said this before, any kind of change, whether it doesn't matter, pressure, volume, number of moles, is always products minus reactants. So 1 mole of gas here, 3 moles of gas here, so our delta Ng is 1 minus 3, which gives you the minus 2. Okay, so Kc is Kp divided by RT to the minus 2 power. Okay, I simply took the equation that I gave you and rearranged it to solve it for Kc. Okay, rearranged it to solve it for Kc, and then this becomes Kp times RT squared, right? And let's get rid of the divided by, because dividing by RT to the minus 2 power is the same thing as multiplying by RT to the second power. Right, so you take 3 times 8 to the minus 2, which was Kp, okay, times RT, so 0.08206 times 473. Remember to be consistent with units. The temperature has to be converted into Kelvin, right? So 473. To convert Celsius into Kelvin, you add 273, right? So 200 Celsius plus 273. That's how you get the 473 Kelvin. Multiply, and it comes out to be 57.2. So if you have more gaseous products than reactants, Kp will be bigger than Kc. Okay. If you have more gaseous reactants than products, Kp will be less than Kc. And big surprise, if you have equal moles, then Kp is equal to Kc, right? Because if you have equal moles, what's delta Ng? Delta Ng is going to be 0. And basically then the RT term, this term becomes 1 because it's raised to the 0 power. So Kc is equal to Rp. So let's say we had a reaction like this. If we had a reaction like this, H2 plus I2 makes 2Hi. Okay. Then we have 2 moles of gas. Well, let's assume all of them are gases. If we have 2 moles of gas here and 2 moles of gas here, delta Ng is 0, and Kp would equal Kc. Okay, we will stop here for the first part.